Namaste and a very, very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun, and in today's presentation, we'll be looking at a popular and widely used technique called as the curve estimation. Curve estimation is most appropriate and useful when you want to compare a linear model with any other model. Many times we assume that the linear model is the most appropriate model for the data that we have, which may not be the case. There are other models which may fit the data a lot better than the linear model. To explore this further, what I will do is I will practically demonstrate what are the benefits of using other models vis-a-vis the linear model. I will be using a data set which is called as the advertisement data set, which is part of SPSS sample files. Let me click on File menu. The second option here is Open. The very first item here is Data. When you click on the option Data, you see a whole lot of files under SPSS sample files. I will be choosing the fourth file from the top, which is called as advert.sab. Let me open this particular file. It's a very simple data set. You have two columns. There is a retailer who wants to study what is the impact of advertisement on sales. I repeat, the problem statement here is to study what is the impact of advertisement on sales. So you have information about advertisement and sales. To understand this further, let me click on variable view. It simply says the first variable advert is about advertisement spending and the variable sales is date-ended sales. Now, since I want to predict sales, I can use sales variable as the dependent variable and advertisement as the independent variable. I want to compare between two models and impress upon you what is the performance of the linear model vis-a-vis the other model. To perform the curve estimation, what we have to do is click on the Analyze menu, choose the linear option. Within this, you have a whole lot of options. Please choose the third item from the top, which says curve estimation. There's a new dialog box which pops up. You see the dependent list, and here you can specify the independent variable. Since sales is the dependent variable, I will push this variable under the dependent list. And when it comes to advertisement, I will push this along the independent list. What I would like to do here is build a simple linear model. Curve estimation offers 11 different options. First, linear model. Second, quadratic model. 3, it offers compound. 4, growth model. 5, logarithmic. 6, cubic. 7, S-shaped model. 7th, exponential. And then you have inverse model. You also have power and logistic models. So these are the 11 different models that SPSS offers: linear, quadratic, compound, growth, logarithmic, cubic, S-shaped models. You have exponential, inverse, power, and logistic. I will not click on any of these options initially. I will go with the default linear model. If you want to include the constant, make sure that you tick this option. If you want a plot of the models, again, please make sure that you tick mark this particular option. Let me click on the option OK. In the output window, you can see the results of the SPSS curve estimation procedure. This is what the linear regression model says. You can see the distribution of the data points. This is the observed data. Along the x-axis, we have advertising spending, and along the y-axis, we have the sales variable. What does the linear regression model say? The linear regression model says, and you can see here a straight line, and it keeps going up. The linear regression model simply says, as you go on pumping money in advertising, your sales will go on increasing indefinitely. That is what the linear regression model says, which is not really a realistic situation, because we know that you cannot boost sales just by pumping money on advertisement. Let's look at the coefficient table. You have the output of linear regression model. The R-square value is 0.839, which is quite good, because it says that 83.9%, roughly around 84% of the variation in sales can be explained by the independent variable advertising spending. You have the F statistic, the corresponding degrees of freedom here, and the significance level is 0.000, which is less than 0.05. Since this is less than 0.05, we can say that the model is significant. It also produces the parameter estimates, that is the intercept and the B1 value. To interpret this output, what I'll do is I will take you to the Word document. This is the same model summary output that you were seeing in SPSS. I've just copied and pasted the same output. Let us just interpret it from Word, because it's a lot easier to interpret the same table from the Word document. You can see here the constant value is 6.58 and the B1 value is 1.01. From this, we can construct the regression equation. The regression equation will simply be expected sales equals, this is the dependent variable, 6.584. This is the intercept term which I'm writing here. I am putting a plus sign here because B1 is positive. 1.071 is the coefficient of advertising. So when you take 1.071 and multiply it with advertising spending, add it with the intercept term, you can get the expected sales. So this is a simple way in which you can construct the linear regression equation. Now, what is the interpretation of the above model? As you can see here, the B1 value is 1.071 and it is positive. This simply says that the B1 value greater than 1 suggests that you should spend as much on advertising as you can, because you'll make that investment back and more in sales. I repeat, you have to go on pumping money on advertisement because you will make that investment back and in fact more in sales. This is the big problem with linear regression model, because we know that this is not true from our own real life experience. Because practically speaking, this does not make any sense for us to go on pumping money in advertisement, because we know that the market has a saturation point. This is very, very important, that the market has a saturation point for advertising, implying initially when you advertise for a product, because of the novelty factor, people may rush and buy money and buy the product. But over a certain point, beyond a certain point, if you increase the spending on advertising, you will see that increased spending on advertising will not have a corresponding increase. It will not see a corresponding increase in sales. Why is this so? Because the market has a saturation point. Beyond this saturation point, increasing the X variable will not increase the Y variable. This is what you were seeing even in the graph here, that as you go on spending money on advertising, linear models say that your sales will go on increasing, which is not true, which is simply not true. The question is, can we better the performance of a linear model? And hence, what I will do is, I will take you back to SPSS data set. This is the data set that I was working on. I will go to Analyze menu, scroll to Regression. The third option from the top is Curve Estimation. I repeat, the Curve Estimation. Let me click on this particular option. A new dialog box pops up. I will unclick on the linear model and now choose the option quadratic. I repeat, quadratic. We know that the formula for quadratic is y equals ax square plus bx plus c. Let me choose the quadratic model and click on OK. SPSS builds a quadratic model and gives the output like this. Now, when you study this output and examine it closely, this fit here is more realistic. Let us go back to the linear regression model. Linear regression model said that as X increases or as advertising spend increases, sales will go on increasing infinitely or indefinitely, which is not the case. Let us look at the quadratic model. What does the quadratic model say? Look at the way it is tracing the path of the distribution. The quadratic model says that as the X variable increases, that is, as you spend money on advertising, the sales increases to some extent, after which it reaches a peak. That is, once sales reaches a peak, it reaches its zenith. No further impact on sales will be found. What you will see is the opposite. That is, sales will hit a saturation point, and beyond the saturation point, if you go on pumping money on advertisement, sales will remain stagnant, and beyond the point, it is likely to come down. Now, I don't see data points after 6 or 7 units here, else we could have been more confident about the path traced here. For all you know, this might be an outlier. It might be a leverage point. We do not know as of now. But coming back to the discussion on quadratic model, a quadratic model gives you a realistic picture that you can see, you can increase the X variable, the Y variable will increase to some extent, reach its peak, and further, after that saturation level, no further improvement is seen. In fact, the Y variable starts coming down. Now, what is this called as? This in economics is called as law of diminishing returns. I repeat, this is one of the classics in economics. It is called as law of diminishing returns, or it's also popularly called as the Miss-Churlick's model. In statistics, we popularly refer to this as asymptotic regression model. I repeat, it is called as asymptotic regression model. This is more realistic than any other, than some of the other models that we are familiar with, particularly in this scenario, because it is able to capture the saturation effect a lot better than some of the other models. To just give you a simple example, imagine that you have a sweet tooth and you love to eat chocolates. So what our common experience is that when you eat the first chocolate, maybe your satisfaction level goes up, which is your Y variable. As you increase, as you put the second chocolate in your mouth, you're more delighted. As you put the third, fourth, and the fifth, you keep enjoying the chocolate. But there comes a point wherein your satisfaction level has reached its peak, and beyond a certain point, let's say 5 or 5.5 in this case, if you pop an additional chocolate, your satisfaction, far from increasing, it remains the same and it starts going down. So this is very, very important, and this is what law of diminishing returns is all about. This is what asymptotic regression model or Miss-Churlick's model speaks about. So in comparison to a linear model, which does not capture the saturation effect adequately, it looks like a quadratic model is a lot better. Further, when you look at the R square value for a quadratic model, you're getting 0.90, which means 90% of the variation in sales is explained by advertising. The remaining 10%, there could be other factors which is not accounted for by this particular model. Compare it with the regression model. Linear regression model explained 83%, whereas the quadratic model explains 90% of the variation. Is this significant? When you look at the p-value is less than 0.05, indicating that the model is significant. One other difference that I'd like to draw your attention to is a quadratic model produces three values. One, the constant value, which is 3.9. Second, the B1 value, which is 2.854, and B2, which is negative 0.245. I repeat, negative 0.245. Please compare it with a linear regression model, which gave you two coefficients. That is, one is the intercept value. It gave you two parameter estimates. That is, one is the intercept value, and the second one is B1. There is no B2 here, but when it comes to quadratic, you will be able to see B1, B2, and the constant. How do we interpret this? To interpret this better, I will take you to the Word document. It's a lot easier to visualize and explain some of these numbers. Look at this. This is the constant term, 3.9. I've just pasted the SPSS output in Word document. I've got B1, which is 2.8, and B2 is negative 0.245. So how do we make sense of these numbers? If you have to construct the quadratic equation, it is simply expected sales equals 3.903. I'm pulling out this number constant and writing it here, plus 2.854, which is nothing but my B1 value, multiplied by advertising spending, minus, this minus is because the B2 value is estimated as negative. We have to square that and multiply it with the independent variable. So this is how the quadratic equation model would look like. Please compare it with the linear model. This is how the linear model looks like, which we built earlier with one coefficient and one intercept. And when you look at the quadratic model appears like this with two coefficient values and one intercept term. Now, how do we interpret the model coefficients? Firstly, when you look at the B2 value, the B2 value is negative 0.245. The negative value for B2 means that this model, that is the quadratic model, suggests that past a certain point, increased advertising would actually decrease sales, which means that the quadratic model is able to capture the saturation effect very well as compared to the linear model. Precisely, if the retailer wants to know at what point should he stop spending on advertising, at what precise point of X would the saturation effect set in, you have to use a simple formula, and that is, please look at the B2 value, which is negative 2.45. Please take it in the numerator, because 2.854, I'm sorry, you have to take B1 value, my apologies. You have to take B1 value and use this in the numerator, divide this by 2 into 2.45. That is, you're multiplying 2.45, which is the B2 value, by 2, taking this in the denominator. That is what you're doing. 2 star 2.45. That will be in the denominator, and in the numerator, what you will be seeing is 2.854. A simple way of remembering this is You take B1, divide it by 2 times B2 value, that would give you the saturation point. That is, you take B1, divide it by 2 times the value of B2, that will give you a number 5.824. Now let us just assume this in terms of dollars. So if you have beyond $5, in fact, to be more precise, beyond $5.8, your saturation effect would set in. So you would want to pump in advertising to the extent of 5.8, because you will be able to see an increase in sales. Beyond 5.8, there is no point pumping in money. So what is the interpretation of the saturation effect of 5.824? Increased advertising beyond the number of 5.824 will actually decrease the expected sales. This is how we can interpret the saturation effect. So we built a quadratic model, and we saw that a quadratic model fits this kind of a situation a lot better. This is not just in the field of marketing. This kind of a model is extensively used in the field of marketing, but not just in the field of marketing, even when it comes to agriculture. If you want to find out what is the impact of fertilizers on the yield of the crop, a linear model there would say that as you go on applying more and more fertilizers, the crop yield would increase indefinitely, which is not realistic. Therefore, Mr. Lick's model simply states, as you go on as you go on applying fertilizers, to some extent, initially you may see an increase, then you see a saturation level, and further, if you go on applying fertilizers, far from increasing the yield of the crop, you will see a decrease in the output. So this is about a quadratic model. If you want to compare both a linear model as well as a quadratic model, let me go back to the data set. I look at analyze, regression, and then curve estimation. Let me click on both of these options and then say OK. So you can compare the observed data with respect to linear model and quadratic model in one graph in this case. Further, you can compare what is the R square between the linear model, which is 83%, what is the R square for a quadratic model, which is 90%, a lot better than the linear model. If you want to further do a deep dive of this data, what you can do is you can generate the residuals. Now, to generate the residuals, what I will do is I'll go to analyze, choose the option regression, and then choose curve estimation. I will unclick the quadratic option and go just with the linear model, because I want to produce the residuals for the linear model. Now, to produce the residuals, what you need to do is click on the option save. Here, you're able to see predicted values as well as the residuals. Please click on both these options, that is predicted values and the residuals. Once you make these selections, click on continue and then choose OK. The specifications would add 2 variables to the data file. OK to save all 2 variables. Yes, I'm OK with that. Let me look at the data set. You can see here, this is the predicted value of sales. The actual value of sales is 12 units. The model, the linear model, has predicted this to be 11. What is the error in prediction? The error in prediction is 0.624. Similarly, for the second case, you see the predicted value is 13 units, wherein the actual value of sales is 11. Now, what inference can we draw from the fit value and the error value? What I'll do is I will make a scatter plot of this and investigate for the pattern in the residuals. To make a scatter plot, please click on graphs. You can choose the very first option here, which is a chart builder. A new dialog box pops up. And as you can see here, you have a list of graphs like bar chart, area, pie chart, you have scatter plot. I will choose the first option, drag and drop to the canvas on the top. It is expecting me to supply the Y variable as well as the X. I will choose residuals along the Y axis, and I will choose the fit value along the X axis. So let us study the distribution of the residuals versus the predicted values. I'll click on OK. Very interesting. You are able to see the distribution of residuals. Along the y-axis, I have residuals, and along the x-axis, I have the predicted value. You can hypothetically draw a curve here. And what is quite clear here is that as the x variable increases, the shape of y initially increases and then it starts decreasing. Let me double click on this, maximize this, right click, and then I can choose the option of add fit line at total. You see a linear model, you see other models like cubic as well as quadratic. Let me choose a quadratic and then apply. Click on close. You can close this particular window, scroll down. What SPSS does is it specifies the quadratic equation model. Now, what you are able to learn from this inverted U shape, you are able to clearly see an inverted U shape here. This inverted U shape that we get when we plot the residuals versus predicted says that there is a pattern which is missed out by the linear model. There is an inverted U-shaped pattern, that is a quadratic pattern in the data, which is not at all captured by the linear model, which further strengthens our belief that the linear model that we produced initially, this is the linear model that we produced, this is not the right model. The right model in our case would be the second model, namely the quadratic model, because that is able to better account for the inverted U shape. Let me just take you back to the graph. This is the inverted U-shaped pattern that we see when we plot residuals versus the predicted value, which only strengthens our belief that a quadratic model is a lot better because it's able to account for this particular pattern as compared to the linear model. With this, I have come to the end of today's presentation. To summarize what we have done in this video, we built a linear model. We looked at the R-square, which is around 83%. The problem with the linear model is that it does not account for the saturation effect. Therefore, to compare the linear model with another model, we built a quadratic model. We saw that when we built a quadratic regression model, the R-square value jumped up to 90%, indicating that a quadratic model fits the data a lot better. Further, to strengthen our belief, we generated the residuals for a linear model, and through the scatter plot, we were able to understand that there is a pattern which is not accounted for by the linear model, and therefore a linear model should not be preferred in this case. We should go by a quadratic model. Many times in the field of marketing, agriculture, and in customer satisfaction, the law of diminishing returns or the Miss-Churlick's model or the asymptotic regression model does a lot better job than a linear model in explaining the pattern of the dependent variable. With this, I've come to the end of today's presentation. I hope that you have liked this particular video. In case you have liked this video, I request you to subscribe to my channel and hit the like button. Thank you very much for watching today's presentation. Have a wonderful weekend ahead.